complex ions. This is the last section of chapter 16, and it's a pretty interesting section. So, although it's not probably the most important section in terms of what you'll see on the exam, it is a little bit different and important. What are complex ions? Well, they are charged species consisting of a metal ion surrounded by ligands. What are ligands? Well, ligands are different substances that are attached to the metal ion, often Lewis bases. Good examples of ligands are water, NH3, halogens like chlorine, and negative polyatomics like cyanide. These ligands have lone pairs of electrons that they can donate in a bond. That's what it is. Remember, the ligand is a good Lewis base. And there's a formation of some constant, some stability. And the equilibrium constant for each step of the formation of the complex ion by the addition of an individual ligand to a metal ion or complex ion in an aqueous solution is what we are looking at. Sometimes what happens is some metals are not very soluble in aqueous solution, like silver chloride that we had earlier, or silver phosphate. These are not very soluble. And how can we make these ions more soluble is by producing complex ions, which are ligand compounds, to make those metal ions more soluble. They do so in a stepwise fashion. For example, here is beryllium with 4 fluorines bonded to it. And what you're seeing here is an addition of each fluoride ion. The fluoride ion, or the F part of that molecule, is considered the ligand because it has electrons it can donate to beryllium, and therefore it could make beryllium more soluble if it formed BeF4 -2 ion. Notice it's aqueous. The number of ligands attached to a metal ion is called the coordination number. So in this final coordination compound, the coordination number is +4 because there are 4 ions of fluorine attached to beryllium. That's a really good multiple choice question. They can look very complex, but if you can figure out the coordination number, that could just be the multiple choice question. For example, here's a cobalt compound with water, and it's that. You notice cobalt is often a solid as a compound, but when it's dissolved in this way, with this ligand, which happens to be water, it forms an ion, which means it can be soluble. The coordination number is a +6, because there are 6 waters attached to cobalt. Let's try one more. AgNH3, 2 + 1. That looks like an I. That's supposed to be a parenthesis. There we go. What about the coordination number for that? Hopefully you see it's a +2 because there's 2 ammonias attached to that metal ion. So there are 2 strategies for dissolving a water-insoluble compound. We already talked about one earlier. If the anion of the solid is a good base, the solubility is greatly increased by acidifying the solution, so we can add it to an acid. In cases where the anion is not sufficiently basic, the ionic solid often can be dissolved in a solution containing a ligand that forms stable complex ions with its cation, which is a good thing. If you can dissolve in a ligand, then you are soluble, and that increases the solubility of that particular ion. So here is a question about solubility. Now your book talks about this on page 762 and 763. So I'm actually going to leave you to read about this section. The idea is silver chloride has a solubility of 1.6 times 10 to the negative 10. Or pardon me, a KSP value of 1.6 times 10 to the negative 10. Earlier, in an earlier video, I showed you that this has a solubility of 1.3 times 10 to the negative 5 molar. Remember, that's where we solve for x. So it's not very soluble. We're saying, gosh, silver isn't very soluble at all. Very low solubility. But if we can attach silver to ammonia, in this case ammonia, it says the solubility of silver chloride in 10 molar ammonia, it can actually form a ligand. And you can see it has a +2 coordination number. And it does so in a stepwise fashion. K1 and K2 show you the solubility of each step. So the steps are pretty soluble. The K value is 2.1 times 10 to the 3. The second one is 8.2 times 10 to the 3. So that's pretty soluble. Much more so than 1.3 times 10 to the negative 5. When you solve according to the way they will show you in the textbook, the answer for solubility of the silver ion is 0.48 molar. And I wanted to just discuss with you briefly the fact that the solubility you can see here is significantly higher than that of the initial solubility, just solving for X way, which is what we did in the intro class. So we can increase solubility by adding different substances that can act as ligands to increase the solubility of these metal ions. You can notice that 4.8 molar is significantly more soluble than 1.3 times 10 to the negative 5. Just to briefly state how you could do that, they will show you how you use the equation. I'm going to have to come down here and do it. Silver chloride solid, which is the solid we're talking about, when it is dissolved in ammonia, notice we have to balance. What we're getting is silver coordination compound, which is aqueous, and chloride ion, which is also aqueous. So we're going to think about products over reactants. This time, however, we have some reactant and some products. It's not a traditional KSP question. We actually have 10 molar of this and no products, but we don't know how much products we're producing. Just like ice, the change column is by ratio, and therefore this is 10 minus 2x. This is x and x. And you would solve products over reactants. What would you equal it to, you might wonder? The K value, which is 2.8 times 10 to the negative 3, would equal x squared over 10 minus 2x. Where do we get that 2.8 times 10 to the negative 3? We get it because we're looking at the total silver ions in solution, which come from this number, which of course is this tiny number, 1.3 times 10 to the negative 5. This number and this number, meaning the silver ion that happens to be in that solution, since they're all ions. So essentially what you're doing is you're taking the KSP value, the Ka1 value, and the Ka2 value and adding them all together, and that's the total amount of silver ions in solution. So that's the K value that you end up with here, but you will be reading about that in your textbook. My focus is to show you that yes, indeed, what happens is the solubility significantly increases when we can produce a coordination compound. So sometimes you'll see questions like this, probably not so much in part 2. There's not a lot of problem solving I've seen on the AP exam, although I will tell you in the 2011 exam there was a question about coordination number on part 2 and the idea of coordination compounds. So it's a good idea to just kind of keep up to speed a little bit about it and to understand it. So if you're faced especially with a multiple choice question, you're able to answer it.